Hi everyone, can you hear me?
Yes, we can hear you and see the screen.
Okay, so let me start. Hi everyone, my name is Sonbol and I'm here with my colleague Lucas, and we are gonna talk about using Olive with ONNX to accelerate generative AI on AMD platform. As it is obvious, we are from AMD. We are proudly presenting from AMD. So let's go to what we have. Can we go to the next slide? So the motivation of our talk is that we are seeing that generative AI models, they are transforming lots of industries, specifically natural language processing and image synthesizers. They are right now everywhere, from healthcare, entertainment, and customer service. But there are some challenges for deploying the generative models in general, specifically if we want to deploy them over locally over DGPU and iGPUs. The reason is that these models, they are usually enormous. They have millions and billions of parameters. That means that we need the high computation for these models, and also they consume lots of memories. So our solution for AMD was leveraging the ONNX and Olive framework to quantize and to optimize these models. Next slide, please. So before diving in details, my colleague Lucas is gonna deep dive in the details. I do the instruction, but the introduction. So before going into the details, I'm gonna talk about the DirectML. So DirectML is a lower level machine learning API, and its building blocks are the operators, like the hardware level operators. And usually it sits in the intermediate level between the apps, like the models is coming, they have the ONNX runtime as output, and the driver that we have. So here in this figure, we can see a software stack of how we do the whole implementation are on AMD platform. Next, please. So as I mentioned, the solution that we have is optimization techniques. So there are different optimization techniques that we can use to deploy these huge models locally. One of them is model quantization. So in model quantization, they usually use lower bit precision data type to represent the whole model. So the structure of the model, the number of the layers, they are the same, but in the lower precision. And the tools that we can use for this optimization, they are Olive and derivatives that's from AMD. The other approach is model optimization, or it's usually being known as layer fusion. When we parse a graph and combine operators into one single large operator. So what's the benefit? It reduces the traffic between the layers, and also it reduces some of the redundant computation that we have. Again, we can use Olive or MI graphics for this purpose. The other optimization technique is using model compilation. So what does it mean is that we have a model architecture, we look at it as a code, and we try to generate CPU, GPU, NPU instruction to fit the model and also target the hardware. So usually in this compiler optimization, we have layer fusion. And there are ERI, MLC, and TVM, there are some examples. But for the experiments that we have done, we focus on model quantization and optimization. So let's go through that, see what's the Olive and how it works. So Olive is a Microsoft framework that's a hardware optimizer from Microsoft. So it gets input models. They can be in the PyTorch, TensorFlow, or other formats. And we pass it to the Olive. Olive, its building blocks, they are passes. So the model goes through different passes, and then we get an ONNX runtime that's suitable for the executive provider that we have, and then we use that on the hardware. For example, for DirectML, the EP is DirectML from ONNX runtime. So about the passes that we have in the Olive, we can have like a ONNX conversion, like quantization, transformer optimization. That's the main one for the generative model, and also tuning. And it's good to notice that what we do in the Olive, the whole optimization is happening offline. So we get a model, we pass it through the Olive and do all the optimization, the ONNX optimization, ONNX runtime optimization offline, and then we use that model for our deployment. Next one, please. So here I'm going to talk about like the experiment that we have done recently. So we wanted to run large language models. For example, here we have example for Phi-3 Mini, and to run them and to optimize them, what we did was we use AWK quantization for weight quantization at the first through the Olive, and also we did layer fusion through the Olive. And when we got the model that's quantized and optimized, we use GenAI DirectML to run them. And here example, as I mentioned before, that's for Phi-3 Mini 4K. If you are more interested to see that what are the steps, and if you want to replicate, I put also our blog post that we published about it. So next, I'm going to pass to my colleague, Lucas. He's going to talk more about the details.
Hello. Everyone hear me okay?
Yeah.
Everyone?
Yep.
Great.
Yep.
I think the Intel talk on neural compressor talked a little bit about this, but what goes into weight quantization. Neural compressor is another tool that can be used through Olive to do these things as well. So, and a lot of what we're talking about applies to other deployment platforms. We're speaking from the Radeon point of view here, but so the idea of weight quantization is to group weights together and have them have a shared scale and shared 0 point so that we can reduce the overall cost of storing these weights in memory. So the idea is that you go from a 16-bit weight in 4-bit quantization, you end up with 4-bit weights, and then a single shared scale. It's usually also 16-bit and a carryover 4-bit 0 point. And then during dequantization, you multiply and add these scale factors together, and you get your 16-bit weight back. And the idea here is that in memory, you are storing less information, less bits, but you still can restore the original information during inference. So looking at what this would look like in a data flow, in an original unquantized data flow, you have your activations and FP16, your weights. You do a matmul and you get FP16 activations out. When in a quantized flow, you have a couple more terms. You have your activation weights, but then you also have a scale factor and a 0 point. So you have 4 memory buffers instead of 2. The compression ratio means that you have a quarter of the memory footprint for your weights because they're all reduced to 4 bits instead of 16. And then your scales and 0 points, actually you have 1 for every n number of weights. So in a quantization ratio, a block quantization scheme of 32, for example, this means that you only have 1 scale factor for every 32 weights, or 1 0 point for every 32 weights. You can change these values. This is just an example. But what this means is that, and then in the ONNX graph today, the way we do this, Olive does this, is it implements this using matmul n bits, which is the representation for this layout. In terms of the compression ratios, an example of what sort of compressions we can get, with an example of a gem weight with 4096 weights, If the original was 8 kilobytes and you quantize it, your original weight's now dropped to 2 kilobytes. And then with 1 scale per 32, you end up with only 256 bytes of scales and 64 bytes of 0 points. So the total overall size is less than 3 kilobytes. Leads to a compression ratio of about 3.4. And this leads to huge improvements in runtime performance and memory cost when running these in inference. So when we run this on our hardware, this is the typical compression ratios that we see. When we go to int4, you see that for something like Llama 2 7B, it goes from nearly 15 gigabytes down to 5. Phi 3 mini and Phi 2 are also smaller models, so you see a slightly lower compression ratio. But this basically means that some models that would literally not fit on commodity hardware are now actually runnable. And along with that, because LLMs are extremely memory bound, typically, especially with batch size 1 inference, you also see a almost equivalent improvement in performance relative to the compression ratio. And this is because you've effectively reduced the amount of bytes you need to move through memory. So even though the computation in this example is still running in FP16, because your data movement is in int4, you have large savings in memory bandwidth costs. And on something like 7900 XTX, which has almost a terabyte of memory bandwidth, this still sees some significant improvements, but where this really shows up is when you run it on something like an iGPU or integrated graphics that's stuck using DDR5, where the scaling is almost exactly linear to the compression ratio. And this also brings the usability of running LLMs on something like with integrated graphics from not usable to exceeding the speed of human reading. So this brings it from not usable at all to something that you could actually deploy. This doesn't come without some issues, though. AWQ is, as a model compression technique, is pretty resource intensive and slow. It parses the model and looks for the salient weights and only quantizes those to preserve model accuracy. This is a heavy process. Other quantization techniques that get you to 4-bit quantization may be lighter and easier, but may come with different costs in terms of accuracy losses. As new operators get added, keeping these quantized nodes up to date and so that they're usable in various ONNX runtime backends is difficult. Requires implementations to keep up. And yeah, I already mentioned that the quantization strategies can impact the compression ratios and the accuracy losses. So picking the right one can be complicated. Though the neural compressor talk earlier had with its iterative tuning approach may be a good way to solve that, actually. So some of the key takeaways: generative AI is everywhere, and getting it to deploy on end user commodity hardware is the next big area for our focus. And so future directions are improving the ONNX runtime backend for DirectML and operator level support for low-bit quantization types and support for different quantization strategies during inference. So I'd like to thank our team that's been putting countless hours into optimizing DirectML for 4-bit inference, and the team at Microsoft for their support and collaboration in developing MapML bits and the Olive runtime to do this quantization scheme. Anybody have any questions?
Hi. Is there an exhaustive list about the backends in ONNX runtime that also support MapML bits? Or is it just DirectML?
I do not know. I can only speak for DirectML.
Okay.
Thank you. Sanbal and Lucas, thank you.